Good evening. Welcome to the fifth of the 8 lectures in the Spring Faculty Lecture Series on the worlds of William Shakespeare. Our subject tonight, the science and the technology of the age. Our speaker from the Department of History at UCLA completed his undergraduate work in science at MIT and his graduate work in history at Stanford. He teaches the history of science and technology here. Among his publications are a study of one aspect of the scientific work of René Descartes, which will be published this year. His current research is on those theories of the nature of crystalline matter which were held by 18th and 19th century scientists. It is with great pleasure I present to you from the Department of History, Professor John Burke. John.
Thank you. Thank you, Dan. That same frenetic, boisterous, and adventurous period, the age of Elizabeth and Shakespeare, also saw the beginnings of modern science. Tycho Brahe, Johann Kepler, William Gilbert, Sir Francis Bacon, and Galileo, whose quadricentennial we will also celebrate this year, all lived at that time. The period, at least as far as science is concerned, has been aptly termed the watershed between medieval and modern times. The main outlines of the course of modern science were charted by the next generation, men born during Shakespeare's time: Descartes, Hobbes, Gassendi, Fermat, and Torricelli. And modern science can be said to have been firmly established in the lifetime of their successors: Boyle, Hooke, Leibniz, Huygens, and particularly Newton, whose views of the philosophy of nature were dominant until the 19th century. It is misleading, however, to emphasize the abruptness of the change by citing merely 3 generations of scientists. Strictly medieval thinking in the natural sciences lasted well into the 19th century, whereas attempts to explain the phenomena of nature with what may be called a modern approach can be found at least as early as the 13th century in Western Europe. The plays of Shakespeare are, of course, saturated with the medieval worldview. The universe was composed of a series of concentric spheres, with the motionless earth at the center of the system. Ordinary matter, the kind we breathe and touch, was confined to the earth and its immediate neighborhood, and this kind of matter was subject to change and decay. The rotating spheres and the stars and the planets that were attached to them were made of another kind of matter, one that was qualitatively more subtle, incorruptible, subject to only one type of change: uniform motion in a circle, because this was the most perfect. Ordinary matter was composed of the 4 elements, ranked in accordance with their virtue. Earth was the lowest of all, then water, then air, and finally fire, which was the highest in the hierarchy. Earth and water had a tendency to fall to the center of the universe, whereas fire and air tended to rise. Each element, then, had its proper sphere, and if the elements were not mixed, there would be a solid sphere of earth underneath a whole ocean covering the entire globe, above which there would be a sphere of air, finally capped by a sphere of fire that would extend to the crystalline sphere in which the moon was embedded. But the elements were mixed due to the motion of the sun, which, in addition to its daily trip across the heavens, also shifts from north to south and back again throughout the year, bringing about the changing seasons. With the elements out of their proper spheres, there was bound to be instability and change, dissolution and decay. The earth could not move. If it did, there would be a constant violent wind. All objects on its surface would be hurled into space. Objects dropped from the mast of a ship would fall far to its rear. Now this system was essentially that which had been postulated by Aristotle in the 4th century BC, and as astronomical observation progressed in antiquity, it required modification. The planets were seen to turn back in their courses. From the degree of brightness at different times, it was obvious that they changed their distances from the Earth. Without interfering with the physical bases of the Aristotelian universe, that is, the central Earth and the uniform circular motion of the heavenly spheres, the astronomer Claudius Ptolemy, in the 2nd century AD, attempted to reduce these observed planetary motions to uniform circular motion by postulating smaller spheres called epicycles attached to the larger or to intermediate spheres. Ptolemy and his medieval Arabic and Christian successors were partially successful in harmonizing the planetary motions with the dictum that they must move in perfect circles. Since the most simple system required over 40 spheres and epicycles, some of which must apparently intersect one another as they turned around, most experts regarded the circles and the epicycles as mere geometrical devices, which had no reality. These formed only the basis for the prediction of celestial events. And within epicyclic astronomy itself, it was recognized that several different geometrical expedients might be used to picture the observed motions. Thus, with physics and mathematics divorced, one could retain a belief in the reality of the crystalline spheres and their circular motion, while accepting the mathematical alternatives for predicting the position of the moon or the planets at any particular time. Christian theology also molded the medieval worldview. God reigned in his empyrean heaven, beyond the sphere of the fixed stars. He had created the universe from nothing and would eventually destroy it. He had planned the universe in every detail. The earth was man's home, and its bounties were for man's use and enjoyment. The various celestial spheres were moved by his agents, intelligences, or spirits, which had their various grades corresponding to the degree of nobility that existed in the celestial world. Thus, the cherubim guided the sphere of the fixed stars, while a lower rank, the angels, were responsible for the movement of the sphere of the moon. On earth, there was man, whose body was generated and which decayed, as did all sublunary substances, but whose soul was created with God's own hands and was incorruptible and immortal. Abroad on earth, too, was Satan and his horde of fallen angels, who by virtue of the supernatural powers that they still possessed with God's indulgence, they were able to tempt man to do evil and to lead him to sin. But there was yet another ingredient in the makeup of the medieval view. Mysticism and astrology had their place, teaching that man's actions and his fate were forecast in the patterns that the planets and fixed stars had registered at the moment of his birth. Events upon earth were determined by the events of the skies. Thus, meteorological phenomena thunder and lightning forecast terrestrial evils, as did the appearance of comets and conjunctions of planets. Now, how could all this be reconciled to man's free will? There were two answers to this question. First, in God's plan, some men were destined to reap the rewards of heaven and others the tortures of hell. Nature, in all of its diverse modes, carried out God's dictates. An event, therefore, that appeared to man to be fortuitous, a result of his free will, was only so because he was unable to penetrate to the remote causes that were operative. He was incapable of following a concatenation of events back to their ultimate source. The universe, in this view, was deterministic, although it appeared that man had free will. Alternatively, it was explained that the stars influenced the lower dispositions of man only, that the souls of men might rise above these conditioning circumstances. But in either case, it was agreed that God, through miraculous intervention, by his arbitrary will, could short-circuit the operations of nature and the dictates of destiny and act directly in a given situation if he so desired. Granted that this worldview contains its animistic, mystical, and superstitious elements, one must nevertheless admit that it does rationalize the perceptions of gross sensory experience. Water exists in a liquid and solid form, and by the application of fire, it apparently changes into air. Earth fuses under the action of fire, and a blast of air promotes this liquidity. The seasons do change with the movement of the sun, and the planting and harvesting of crops are planned with regard to the changing seasons. A rock thrown vertically upward falls back to the same spot on the earth with an ever-increasing speed. The connection between the phases of the moon and the action of the tides had long been noticed by mariners. Peoples become darker as one approaches the tropics, where the sun's rays beat down more strongly. The heavens do seem to revolve around the earth. Our bare senses give us no evidence that the earth moves. Now, how was this ossified pattern broken apart and almost completely swept away within the relatively short period of 150 years? From Edmund's speech in King Lear, we see that the cracks in the edifice had already reached the popular level when he says, "This is the excellent foppery of the world, that when we are sick in fortune, often the surfeit of our own behavior, we make guilty of our disasters the sun, the moon, and the stars, as if we were villains by necessity, knaves, thieves, and treachers by spherical predominance, drunkards, liars, and adulterers by an enforced obedience of planetary influence." This is a bold denial of the medieval worldview. In fact, the entire scientific revolution seems characterized by a polar change from a servile dependence on gross sense experience, moderated by the dogma of authority, revealed or otherwise, in the formulation of our view of nature, to the confident assertion that it is within the capacity of human reason to discover nature's laws and principles. Historians of science offer many explanations to account for this change. One view is that the roots of the scientific revolution can be traced back to the medieval philosophers, particularly Robert Grosseteste, Roger Bacon, and William of Ockham, whose attempts to formulate a method of scientific thought that would be applicable to physics finally reached full flower in the late 16th century. In these discussions, the terminology of which shows almost unbroken continuity from the 13th to the 17th century, there is concentration on the ways of determining the causes of events by the inspection and analysis of natural phenomena. There is attention to methods of reducing a plurality of postulated causes by verification and falsification. That is, by testing proposed causes by comparing consequences deduced from them with observation. Now, it is apparent that some sort of method is necessary before science can attain any notable degree of success, that there must be some criterion for fact selection, some statement of cause or theory, and some reference to observation or experiential test to substantiate theory. Close observation of scientific works, even at the end of the 17th century, seems to indicate that these elements of a successful scientific method were only beginning to be understood by the majority of actual working scientists at that time. I believe that the effects of these medieval discussions may be discounted on this basis alone, but one can also point to the fact that the actual scientific achievements of the medieval thinkers were pitifully small. This indicates, I think, that the discussions about method were in the main exercises in logic. There is, however, one notable exception to this denial of the influence of medieval scholastic discussions. This relates to the science of mechanics, rather than to methodology, however. The inquiries into the causes and nature of projectile and uniformly accelerated motion had, by the 14th century, at the universities of Oxford and Paris, reached a degree of sophistication which was unknown in classical antiquity. And it is certain that Galileo was not only familiar with these manuscripts, but profited from them in the formulation of his new science of motion. There is another interpretation which sees the scientific revolution as the culmination of a renaissance in science, which commenced about the mid-15th century. According to this view, during the following century, the complete corpus of the ancient classical texts became available through the accurate translations of the humanists and were widely distributed through the medium of the newly invented process of printing. Once these texts were explored, digested, and criticized, it is said, the field was cleared for real progress in the sciences. One difficulty of this interpretation lies in the explanation of why there was not a scientific revolution in antiquity, and why the transmission of this corpus of Greek and Hellenistic science to the Arabs did not have a leavening effect upon this vigorous culture in its prime. In other words, why the revolution took place only in Western Europe. Nonetheless, the interpretation has many merits. There is no question but that Copernicus, in his formulation of the heliocentric theory, published 20 years before the birth of Shakespeare, was greatly influenced by the speculations of the Pythagorean Philolaus and by those of Aristarchus of Samos in antiquity. Galileo undoubtedly patterned his kinematical demonstrations on those which the great mathematician Archimedes had used to determine the principles of statics in antiquity. One reason that Kepler was successful in his study of planetary orbits was that he was completely familiar with the work that Apollonius of Perga had written on the properties of conic sections. The ancient atomic theory of Epicurus became current in philosophical speculations soon after the discovery of the complete text of Lucretius on the nature of things in the early 15th century. And it was transformed into the corpuscular theory of matter in the 17th century through the agency of Pierre Gassendi and Robert Boyle. There is still another fruit of the classical heritage, mathematical idealism, which is so apparent in the 15th century works of Nicholas of Cusa and in those of Galileo and Kepler a century and a half later. This is a metaphysical belief, an a priori statement concerning the nature of the universe, that the basis of the universe is mathematical, that God is a geometer. Although this is usually termed Platonic or Neoplatonic, the belief was voiced at least as far back as the 6th century BC, when Pythagoras' discovery of the relations between the lengths of taut strings and the notes they sound when plucked led him to this conclusion. Perhaps it is best expressed by Galileo in his famous treatise, The Assayer, when he writes, "Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language and read the letters in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures without which it is humanly impossible to understand a single word of it. Without these, one wanders about in a dark labyrinth." Kepler was led by this metaphysic to postulate for a time that the orbits of the planets were either circumscribed around or inscribed in 5 huge heavenly structures that corresponded to the 5 regular solids of Euclidean geometry, and that subtle heavenly music emitted by the planets as they wander through the skies, the harmony of the spheres, which Lorenzo describes to Jessica in a beautiful passage in The Merchant of Venice, is part and parcel of this same idea. Now, all of the theories or interpretations of the rise of modern science, which have been mentioned so far, emphasize the change as internal, within science itself, resulting from the impact of prior science, from a newly comprehended methodology, or from a changed metaphysical background. In contrast, there are those historians who stress external stimuli, particularly the influence of medieval and Renaissance technology on the rise of the new science, specifically attempting to show that the impact of the craftsman upon the scholar compelled him to take a new look at things. One theory postulates that mechanical devices that simulated astronomical phenomena and the actions of animals became increasingly so complex and ingenious during medieval and Renaissance times that scholars, notably Descartes, became convinced of that the natural universe of physics and biology was susceptible of mechanical explanation. Mechanical technology of this sort, of course, flourished in Greco-Roman antiquity. The fall of a float in a container from which water was permitted to drip regularly, could be used to turn models of the sun around a celestial sphere, and the production of different sounds could be accomplished by the sudden displacement of air in various sized pipes. Such devices are described by Vitruvius and Heron of Alexandria at the beginning of the Christian era. The latter is said to have constructed a bird that moved and sang. Such mechanisms were present in the Arab world, in Byzantium, and in China during the Middle Ages, and the tradition was transmitted to Europe without much change during the medieval Renaissance of the 12th and 13th centuries. But once in Europe, it had a remarkable development. Richard of Wallingford constructed a clock about 1320, which was adapted to demonstrate the principles of Ptolemaic astronomy. Later in the same century, Giovanni da Dondi built a great clock at Padua, and the first of the most famous clocks at the Cathedral of Strasbourg was constructed in 1354. There, a large bronze automated rooster presided over the clockwork, crowing and moving on the hours, while other mannequins performed tasks, and a calendar kept track of events in the heavens. From this time on, astronomical clocks become the features of the great cathedrals, and there is evidence that some automata, mechanical men and apes, were constructed during the next century. Leonardo da Vinci is reported to have made a mechanical lion, which paid homage to Louis XII of France on his entrance into Milan by baring his breast and displaying the king's armorial insignia, which was emblazoned thereon. The increasing ingenuity of these devices, it is said, not only provided the basis for the manufacture of instruments upon which the progress of science depended, but also gave confidence that the world of nature, both animate and inanimate, might be explained in terms of matter and motion. The success with such devices, it is said, led to the next phase, which was the attempt to simulate rational thought, as evidenced by the construction of the first true digital computer by Blaise Pascal in 1645. When one reads certain portions of the work of René Descartes, one can agree that the theory is credible. But it is equally likely that Descartes' theories were primarily motivated by his consideration of the atomic theory of matter. The link between the scholar and the craftsman on this basis, I believe, is at best tenuous. There is also the view that the craftsman influenced the scholar by instilling in him the idea of progress, which is central to the development of science. The first clear expression of the ideal of progress in the sciences was made by Sir Francis Bacon, who preached that scientific knowledge could only be gained step by step through the contributions of generations of scientists who built upon and amended the findings of their predecessors. Bacon asserted that the aim of the true scientist should be to aid this development for the benefit of mankind. In support of this view, it is pointed out that the idea of progress was foreign to the medieval scholastics because of their reliance upon revelation, or because they believed that their systems were logically complete. The humanists, it is said, did not stand for progress, but rather considered that the works of the classical authors were unsurpassed and should be used as models. On the other hand, from the more literate and successful artisans of the late Middle Ages and the Renaissance, there came an increasing harvest of treatises on perspective, architecture, gunnery, fortification, navigation, mining, surveying, instrument making, in which there is often expressed the intention to further the craftsmanship of their contemporaries and successors by writing about their own achievements. These works, in the main, were written in the vernacular, and continuing emphasis was placed on cooperation to extend knowledge. According to this theory, then, modern science was born when academic learning and the attitudes of the artisans joined forces roughly about 1600. But this view has been oversimplified. I have already cited the continuing tradition of medieval mechanical discussions. And among the humanists, for example, one can cite Erasmus, Vives, and Petrus Ramus as champions of progress. Now, what of the actual technological advances themselves? The effective use of gunpowder dates from about the mid-15th century, and it brought in its wake a host of problems, at least for the intelligent artisan. The development of the iron industry was intimately connected with the development of guns, which in turn led to increased practical knowledge in the areas of mineralogy and metallurgy. The menace to fortresses led to increased attention being given to architecture, to the construction and design of buildings. The problems connected with the path of a projectile involves the laws of falling bodies, the effect of gravitation and wind resistance, and the many related physical phenomena which together make up the modern science of ballistics. And in the medical area, there were developments involving the proper treatment of gunshot wounds. There is the objection that innovation in armaments in the past did not stimulate the rise of science, which is certainly true. Nevertheless, one is struck by the empirical content of Galileo's dialogue concerning two new sciences, which in large part is devoted to problems of projectiles discharged from guns. The invention of printing was another mid-15th century technological innovation, and about 10% of the publications in the first century of printing were devoted to sciences. With a widespread diffusion of observations, theories, and pure speculation, with the opportunity for criticism and the appearance of clear illustrative material, it was undoubtedly a stimulus toward rational science. More directly, it compelled the gradual adoption of simplified and uniform symbolism in mathematics. It seems to me that the great voyages of navigation, which commenced in the mid-15th century and lasted, of course, through the Elizabethan period, deserve more attention than they have heretofore been given by historians in accounting for the rise of science. For one thing, they destroyed the ancient fables of the boiling hot tropical seas, of the mountains of water in remote parts of the globe, which were necessary corollaries of the Aristotelian physics to explain why the known land masses were above the sphere of water. The Antipodes were found, contrary to Christian belief, to be inhabited. the magnetic mountains of lodestone, which pull the nails from passing ships, thus sending their unsuspecting occupants to watery graves, were recognized as mythical. More directly, however, the crossing of the equator in 1474 by the Portuguese meant that mariners could no longer find their latitude by sightings of the North Star. Astronomers were compelled to devise new methods incorporating solar observations. The determination of longitude, of course, long remained a problem, but astronomers attempted to solve its measurement by recourse to lunar observations, and after Galileo had discovered the moons of Jupiter, by the computation of the eclipses of these satellites. In another area, the whole science of terrestrial magnetism developed from the observation of phenomena associated with a compass. One need only glance at William Gilbert's great work on the magnet to see the influence of this empirical tradition. From Peter the Stranger of Maricourt in the 13th century, who first described the pivoted compass, through the Portuguese and Spanish navigators at the turn of the 16th century, who discovered magnetic variation, to Robert Norman, Gilbert's older contemporary, the master of one of the ships that withstood the Spanish Armada, who first detected magnetic dip. It is true, as Galileo complained, that Gilbert did not apply mathematics to the science. This was asking too much of Gilbert, of course, but he did see magnetic phenomena as incorporating a force, by reference to which they might be explained. And he assembled the observed data into a fairly rational descriptive theory, which was characteristic of the new scientific approach. These, then, are some of the interpretations given to account for the rise of modern science. Although no one view is likely to be completely satisfactory, together they do illustrate the trends, the forces that were operative prior to and during Shakespeare's lifetime. They affected students of nature in such a way that the entire fabric of the medieval world picture was torn to shreds. A new kind of rationalism was produced, which was to have the ultimate effect of changing drastically man's attitude toward and his explanation of his physical environment, and even of his own nature. Let us review the principal events that occurred during the Shakespearean era that served to undermine the medieval worldview. Copernicus, who died in 1543 in the same work that his great work, on the same year that his great work on the revolutions of the heavenly orbs was printed, was led to endorse the ancient heliocentric theory by an aesthetic dissatisfaction with certain aspects of the Ptolemaic astronomy. His system was mathematically no simpler than that of Ptolemy, but it was more reasonable in its explanation of the apparent retrograde motion of the planets and of their varying brightness. However, he clung to the idea of uniform circular motion, so that he was forced to maintain the fiction of epicycles. Further, he still believed in the existence of a sphere which contained the fixed stars, which, however, he was compelled to move to a tremendous, an unbelievable distance from the Earth. Otherwise, an observer on a moving Earth should be able to detect what is known as stellar parallax. the apparent angular displacement of a star measured from 2 points of the Earth's orbit. Copernicus, it should be noted, did not venture any physical proofs of his theory. He gave no reasons, for example, to explain why objects were not thrown off this rapidly whirling planet. He merely insisted that it was more reasonable to explain the apparent diurnal motion of the sphere of the stars and of the sun and the erratic movements of the planets by postulating a moving Earth than it was to assert the fixity of the Earth. The great Danish astronomer Tycho Brahe can be cited as an example of the merger of the craft and scholarly traditions. With a university education, Tycho took the trouble to design his own instruments. He insisted on precision and accuracy of observation, and he studied methods of estimating observational errors and attempting to correct for them. In 1572, a nova suddenly appeared in the constellation of Cassiopeia. It was brighter than the dog star Sirius and even the planet Venus, and it gradually dimmed and was extinguished after 18 months. Tycho made many observations of this nova, disturbances from which, incidentally, can now be picked up by radio telescopes, and he could detect no parallax. Thus, the star had to reside in the firmament itself, which was heralded as proof that change does occur in the heavens, a direct contradiction of the Aristotelian dictum that the heavens were incorruptible. But yet, Tycho could not accept the heliocentric theory. With the best instruments that could be manufactured before the advent of telescopic astronomy, he could not detect a stellar parallax of even 1/2 a minute. This had the effect of removing the sphere of the stars to a distance of some 26 billion miles, and would, in turn, given the apparent stellar diameters of 2 minutes, have made each of the stars larger than the entire system of the sun and planets extending out to Saturn. These considerations motivated him against accepting the Copernican theory of the motion of the Earth. Such a tremendous distance between the planets and the stars, he considered, would have been wasteful on the part of the Creator. He could not know that the actual distance of the nearest star was some 1,000 times his estimate, some 26,000 billion miles, nor that the apparent diameters of the stars give no idea of their true sizes. But as a result, he developed his own planetary theory, that the sun and moon revolved around the Earth, while the remainder of the planets revolved around the sun. This is mathematically the same as the Copernican system. And because there was an intersection of the planetary orbits in the system, it destroyed the idea of the crystalline spheres. So, even while discarding elements of the Aristotelian Ptolemaic astronomy, Tycho was unable to adopt the views of Copernicus. The Tychonic system, in fact, became quite popular among the more conservative astronomers at the time. It was well received in England, for example, and continued to be held there until at least 1650. Johann Kepler was conceived on May 16, 1571, at 4:37 a.m., and was born on December 27th at 2:30 p.m. after a pregnancy of 224 days, 9 hours, and 53 minutes. Now, the reason that we know these intimate facts is that they appear on the horoscope that Kepler cast for himself. It is important in that it clearly displays how the greatest scientists can be prisoners of the thought of their times. Both Brahe and Kepler were working astrologers, although it appears that both held qualifications about the efficacy of astral influences in their later years. Not so with William Gilbert, however. He remained firmly convinced of the truths of astrological doctrines, which may not have impressed good Queen Bess, whose physician he was at her death. With Kepler, we can discern clearly the Pythagorean mathematical idealism that infected the thought of the Renaissance. But at the same time, one finds in Kepler the dogged determination to search for the truth. Kepler knew that Tycho's observational data were necessary for the construction of a rational mathematical theory of planetary motions, so that it was no idle quirk of fate that brought Kepler to Brahe. Kepler wrote, "I confess that when Tycho died, I quickly took advantage of the absence or lack of circumspection of the heirs by taking the observations under my care, or perhaps usurping them." When Kepler was through with his mathematical analysis of Tycho's observations, the main features of even Copernican astronomy had changed. The planets now revolved around the sun in elliptical orbits. All of the epicycles had disappeared. The planetary distances were mathematically related to the periods of their revolutions, and their changing speeds were seen to be proportional to their changing distance from the sun. To explain the elliptical orbits, Kepler postulated a real force emanating from the sun. In fact, it was Gilbert's magnetic force. But even Kepler could not accept all of the implications of his new astronomy. The stars, though tremendously remote, were still in a fixed shell. The universe was still finite, and man, though pushed out of his central position, he considered to be still favored by God, as being on a planet that was midway between the sun and Saturn. It is with Galileo that we may clearly see that unusual merger of the various traditions concerning which I have spoken. He was well acquainted with the work of his medieval predecessors in mathematics. He was imbued with mathematical idealism, although he did not approach the mysticism of Kepler. He had a complete grasp of the method of Archimedes, but yet he had the talent, the shrewdness, and the inquisitiveness of the artisan. With only hearsay knowledge, he constructed his own telescope and turned it on the heavens to dispel forever, with his discoveries, the fiction that the matter of the heavens was incorruptible. There are mountains on the moon. The sun has spots, which by their changing shape indicates that the sun itself rotates on its axis. Venus has phases, just as our own moon. And Jupiter has a group of moons, a planetary system in miniature. But also, with his studies of the motion of bodies, Galileo was able to erect the foundations of a new physics, one that could demonstrate that the motion of projectiles and that of freely falling bodies adhered to the same laws, and from which later Newton could derive the laws of universal gravitation. The props that held up the old Aristotelian physical theory were completely cut. The great achievement of Galileo, however, was to extend the Archimedean method to the science of motion, giving it mathematical rigor, to establish the universal validity of such a science. and in so doing, to demonstrate that mathematics was the language of science. It is important to realize, however, that Galileo's achievement was conceptual as well as mathematical. He arrived at conceptual definitions of such physical notions as inertia and acceleration. Thereafter, because of Galileo's success, it became a goal of scientists to give science a mathematical structure by framing adequate concepts, pressure, mass, momentum, and so on, which were capable of mathematical definition, and simultaneously to devise new mathematical techniques by which these concepts could be successfully manipulated. With the removal of the stars to tremendous distances, the fiction of direct astral influences faded away. Not completely, however, for stocks are still bought and sold on Wall Street on this basis. And the celestial intelligences and spirits were put out of work when the laws of universal gravitation were propounded by Newton. The planet Earth was displaced from the central focus and became just another one of the lesser bodies in the myriad that populate the universe. This awesome and perilous, yet somehow comforting and beautiful romance that was the medieval worldview was swept away. We have not found another synthesis to replace it, and perhaps we never shall.